last thing in our notes?
Inner product spaces.
Inner product spaces, yeah, so let's review a tad. I'm not gonna rewrite these vector space axioms. So we had those and commutativity, associativity, all that good stuff. Point is that vectors as arrows satisfy all those. Okay, three-dimensional vectors, and I have there's some vector presentation I didn't do, but we'll catch up with that. We have plenty of time to do more vector stuff. So we'll repeat these inner product space points and then move forward. We want to make it into function spaces and come back to our Fourier series with a new view of those things. Okay, so let's give this a try. I'll start with the inner product again. And then we'll take it from there. Okay. So we've got the inner product. And we'll already use this expression here. And it takes a space, takes two vectors, and turns them into a number. And so this field here, so-called, is going to be the complex numbers. Could be the real numbers, could even be the rationals, could be the complex numbers in general. And you've got these three properties. Yeah, I'm just going to say x and y are elements of the vector space. So x and y are vectors, alpha, beta, lambda, are numbers. Okay, think complex numbers. And then we have x, y equals yx star, complex conjugation. The second one is x lambda y plus mu z. So what you have here is the linearity in the second term. So lambda x y plus mu x z, and then the third property is that this inner product with itself is positive and equal to 0 only when x itself is that 0 vector. Okay? So the first thing to check is our standard dot product complex version. So check with the complex inner product. In fact, if we were to check with the real one, it'll be a subset of that. It'll work. Okay. So what we're going to do is say we've got A equals A1 to AN. B equals B1 to Bn. Okay. So we've got n tuple, n could be 3, and then it would just be an arrow in free space. So A dot B, we have to implement this rule where we have A1, B1, A1 star B1 plus A2 star B2 plus A3 star B3 plus and so on. Or you would say A sub J star B sub J, J equals 1 to N. So this could be the A, B, like that. That could be the same expression. complex conjugate of this. Complex conjugate of this. And then you're complex conjugating each one of these summands, so A star, B, J, and J, complex conjugating those, and you end up with A, J, sub J star. So that is equal to B, A. And that's that property right there, okay. Now, what if you have real numbers instead of complex numbers? Then this is trivially fulfilled, right? Star and the non-star is trivially fulfilled. Okay. So that's the one property. Yeah, the other ones are gonna hold true as well, okay? With this A and B, so this would have been 1. And property 2, so we could have had A, this time we'll go like this, lambda B plus mu C. Comma with it. And we would be summing over this, we'd have A sub J lambda. So put the star on the A there, lambda B sub J plus mu C sub J. And just work our way through. Itself, you have to have that complex conjugation. Yeah. I'm just gonna write here, you know, we've got A with itself, you want that to be real and positive. I'm gonna write down here, you've got to have the AJ star, AJ. That turns into the sum of the A sub J complex conjugate J equals 1 to n. So that's the property we had at the very beginning when we studied complex numbers. You're just inheriting it and implementing it over a whole sum of these things. Good. So that may be reiterating what we've done before, but I just want to make that point. Everything we've done with vectors as arrows, we're maintaining right here. So let's keep this up here. And the next thing, I'm going to erase these. The next thing is the norm. And the norm just generalizes the magnitude of a vector. In fact, if you just have vectors as arrows and ordered tuples and stuff, you don't really need this next level of abstraction that we're going into, but we'll need it soon enough. Okay, so, but we're gonna keep working with the arrows for the moment. Okay, so the inner product generates a norm. What is a norm? Okay, so we've got a norm here. And if x is a vector, then we use these double lines. It's essentially a magnitude. And you can take that as the square root of the inner product with itself. And in fact, just think of the magnitude of a vector or a number. Okay, and here are the properties of the norm. It's always greater than or equal to 0, and it equals 0 if and only if x is the 0 vector. The second property is that if you take lambda x, remember lambda can be a complex number now, then you have lambda magnitude times the norm of x. Okay? A lot of vertical lines right there. And the third property is called the triangle inequality. So the norm of a sum is less than or equal to the sum of the individual norms. This is something we have with numbers. And so we'll know this triangle inequality. Good. So what we're going to do is demonstrate these, but we have to demonstrate them using the properties of the inner product. You know, we can say we have these just for numbers, but we're not just talking about numbers, we're talking about objects that satisfy these conditions. So I'm gonna have to erase this, but I'm gonna use those properties. Okay. First one, greater than or equal to 0 with 0 only when. So we can just do the norm squared to get rid of the square root there. Inner product of itself. And because of the definition of the inner product, that's equal to complex conjugate of itself as well. Because I'm just reversing the order of the identical. And this tells us x squared real and positive. So we get that from there. Second one, we've got this lambda x norm. So we go into the definition here. We've got lambda x. Okay. So the square root of inner product with itself. We've got the square root of, when we pull this one out here out front, it comes out as a lambda star, and the one in back comes out as lambda x. Okay. And the square root of lambda star lambda is the magnitude, complex magnitude of lambda, and the square root of the x with itself is the norm of x. So we just use the property of the scalar product for this. Now the last one takes a little bit more doing to get it started. So the triangle inequality, this one's interesting. So let's go ahead and just start with the left side. Okay. But we're just going to square both sides. If it holds true for the squared, holds true for this, and that gets rid of that square root there. So x plus y squared is the scalar product x plus y, and we can just expand these out. So we've got x plus x, y. We gotta maintain the order though, plus yx plus y. So these two are x squared plus y squared. Well, what about this thing in the middle here? This second one is the complex conjugate of the first one, right? So I've got xy and yx, so this would be xy plus xy complex conjugate. And a complex number plus its complex conjugate is equal to 2 times the real part of this xy, this complex number. Okay, so far so good. I erase the top lines over here. This is the one we're trying to prove. Triangle inequality. Okay, so let's hold on to this for the moment. Actually, this one, I could say x plus y squared less than or equal to x squared plus 2 x y plus y squared. So I have to compare those two. So what I have to compare is the red circled one here and here. And this is what we're trying to prove. So triangle equality is true if two real part x, y is less than or equal to 2x, y. Real part x, y less or equal to x, y. So if these were just numbers, we'd already declare victory. Okay. Or if this were, if we could just call this the standard dot product, we'd say, yeah, this, these could be orthogonal, be less than the two, could be less than the two magnitudes, yeah.
With the norm of lambda x, why does one of the lambdas pull out as the complex conjugate of lambda?
That comes from the property, comes from this property. The second one pulls out as lambda itself, right? And the complex conjugate of the entire thing. So if you take the two properties, so this one came out as that, and then if you take lambda x, if we want to do that one, okay, star is equal to x lambda x is equal to lambda x x. That means if you pull this one out as lambda star x star, you get lambda x. So it comes from the linearity in the second term and the fact that when you complex conjugate the whole thing, you reverse the order. Good, so we just have to prove this. This is the Cauchy-Schwarz inequality. So do we have to prove that separately? True, so we have to prove this. That takes a separate proof, but I'm gonna give that in a second here. Yeah. That's a special case of the Cauchy-Schwarz inequality. Cauchy-Schwarz inequality. So I'm gonna do the Cauchy-Schwarz, and then we'll apply this stuff. And then we'll see that that's a special case. That says that the magnitude of this xy squared is less than or equal to x squared y squared. So you could take the square root of both sides. We take the point of square root of both sides. We're saying that this scalar product is less than the product of the two magnitudes. Okay, essentially what we're saying. And here we just have to show that the real part is less. So that'll follow immediately from Cauchy-Schwarz. Okay, so let's see. There are a number of different proofs of this one. It's kind of famous. So this is just one possible construction. So the proof is let z equal x minus xy times y, okay. And this is a construction where z is perpendicular to y. Because if you take z dot y, or z into y, okay, inner product, then you get x into y, you get minus x into y into y itself divides out, okay? So this is just a construction of a perpendicular component. So now we'll solve for x, which is just x, y over y plus z and y are perpendicular, therefore we can apply the Pythagorean theorem. So Pythagorean theorem, x squared itself. Nope. I'm gonna square this. Squared. So I multiply top and bottom by y after x y plus. So this here is y to the fourth. Let's keep going here. So we have x, y squared plus c squared greater than or equal to squared y squared. And then we cross multiply over, cross multiply y squared over here, and we get the Cauchy-Schwarz inequality. Good. So I want to do the application that we're kind of here for. So these hold true for arrows, that's fine. What we want to look at is function spaces. So next, consider functions f of x on minus pi to pi. Is that next door?
Yeah, it's on the other side.
Plane. You guys can complain too.
I thought he was gonna knock back.
Okay, once more with feeling. Okay, we have these properties, and we want to return to our Fourier series with some added insight. So let's clear the board and set this up here. Okay, I'll link the faces. So here's what we're gonna do. So this is what we were heading for. Let's look at continuous functions. Continuous functions minus pi to pi. Okay. And they can actually be, they can be real or they can be complex. So this takes us back to our study of Fourier series. Okay, so we were on minus pi to pi. We learned we can extend this, into the entire axis. So, and these were the things that we could draw like that. Okay. So we have equals f of x. And we could even have, we can do more than we had at the beginning, we could also say that would be u of x plus I times z of x if we wanted to. In other words, it could be a complex function, or we could just say, you know, f of x can be a complex number. So this is a sufficient definition of continuous functions on minus pi to pi to assert that those are vectors. So f, g, h, f of x, g of x, h of x are vectors. So what does that mean? They're not arrows, but why could they be considered vectors? You have to dial back. I'm not going to rewrite those definitions. You have to go back to the definitions 1 through 8, and you just check them off one by one. Addition, multiplication, etc. Okay. So let's put here because they satisfy what is called vector axioms. Axioms 1 to 8. Okay. So example. Remember, the definition is they're continuous functions. So I take f, and I take g, then f of x plus g of x is also a continuous function, right? It's also a continuous function. For example, if we're talking arrows, you know, vectors, we can say, suppose I have, you know, A and B, these are these two vectors, and you know, A plus B equals this plus that, I'll even do the result is here, right, is also a vector. And then likewise, lambda f is also a continuous function. So apparently the space of functions, you know, the functions or vectors, they comprise the space. The space of functions means they're continuous on minus pi to pi. So if you go through all of your vector axioms, you'll see you just check them off 1, 2, 3, all the way through 8, and that's what it takes to be a vector. Okay. So far so good. So what did I say? Because they satisfy vector axioms 1 to 8. So what about the inner product? If these are vectors, do they have an inner product? Okay, I'm going to go ahead and erase this right here. So the inner product, and this is the perfect example to begin with, inner product FG is equal to 1 over 2 pi integral minus pi to pi f star of x g of x dx. Okay. Or why am I doing the 1 over 2 pi? Because we're going to look at Fourier series. But more generally, you wouldn't have to actually have the 1 over 2 pi. You could just say f g is equal to integral minus pi to pi. We'll see how that changes or doesn't change things. Okay. So this is parenthetically. Okay. So what's going on here is consider f of x equals e to the I k x. We've been here before. So now f equals 1/2 pi times pi e to the minus I k x g of x dx. And what is this? This is a Fourier coefficient of this particular function g. So this is just c sub k for the series expansion g of x equals sum over c sub k e to the I k x k equals minus infinity plus infinity. So we had an inner product all along when we were doing Fourier series, we just didn't know that we had a function space. And then the norm that's generated by the inner product is also going to be there. Okay, so this was our series that we remember doing quite a bit of work with. And I'll put down the norm as well. So the norm and I'll use that letter G for the moment, is equal to G into itself square root. So we're looking at the square root of 1/2 pi minus pi of pi. And then we would have G star of x, G of x dx. And of course, G star of G is going to be positive, definite, real positive. And that's the norm that's induced by the inner product. So if this thing really satisfies the inner product axioms, which we gotta check, then we know we have a norm, so it's become magnitude. Okay. Should we check those axioms? I think so. Good. So that's where we're headed. We have to check the inner product axioms. So check inner product axioms or definition. So go back to those. Like I said, I'm not going to do all 8 of those other ones, but we have f g is equal to g f complex conjugate. So that was one of them, and you can even see it right off the definition, right? If I reverse the order of f and g, I'm reversing the one that got a complex conjugate. So that one is trivial. And then if I have f lambda g plus mu h, and it's supposed to be lambda h, and we go up to this thing here, this definition, doesn't matter which one we use, okay? Because the first one is the one that's being complex conjugated. If I'm multiplying the second one by lambda and u, those are pulled out linearly, okay? No complex conjugation. So again, this one works as well. And then the third one, f greater than or equal to 0 and equal to 0 if and only if f is identically equal to 0. This one leads to some interesting and tricky situations, okay? Namely, what constitutes a function being strictly 0? So there you actually have to dig in a little deeper. As long as it's a continuous function that you can draw with your hand, so to speak, then this is going to be trivially fulfilled. What you can have is, I'm just going to put a note here, because it would seem trivial. You can also define functions that are 0 everywhere, except at a certain point. Okay. And you can even have a whole bunch of those points, and that you integrate. These have measure 0, so the integral of this times some other function is still going to be 0. Okay. So those details we're not going to really bother with, but you want to be aware of them. But yeah, other than that, this inner product does exactly what it's supposed to, and as such, it's going to generate a norm. And we can do, as we'll see later, we can do linear algebra with these things. Let's go back to the continuous functions on the integral to the Fourier series. We've got a couple of good things here. So what you can see here, if we go back to this expression, the one that we're familiar with, is that there are basis vectors. There are orthogonal basis vectors. So the next thing we have to look at is, what is orthogonality, say, at f and g? When are f and g orthogonal? Okay, they're orthogonal if they're arrows, when they're at 90 degrees to each other. Okay, if they're functions, they're orthogonal if that integral matches. So let's look at orthogonality next. We have these things well under control here. So orthogonal vectors a dot a equals 0. That's how we're used to thinking of it. Here we have f g 1 over 2 pi f star g, so f of x, g of x, dx equals 0. Well, in particular, we have a set of vectors that form a basis. The vectors e to the I kx form an orthogonal basis because e to the I kx, e to the I, let's just say nx, we're going to take the scalar product of those two vectors. We've got 1 over 2 pi minus pi to pi. E to the, remember the first one gets the minus sign, minus I, it's complex conjugation. E to the I nx dx 1 over 2 pi minus pi to pi. E to the I n minus k x dx. Everybody remembers that, right? So when n is equal to k, we're gonna get e to the 0 of 1 times pi to pi, so it's gonna equal 1, n equals k. And when n is not equal to k, we've done that, and you guys should actually do that some more, right? Make sure you investigate those integrals, 0 when n is not equal to k. So that's a set of orthogonal functions. Now, how many of them are there? How many of those functions are there? Vectors functions. As many as there are natural numbers, integers. So the expansion of this function g over here in a Fourier series needs an infinite number, okay? Needs an infinite number of basis vectors, and that's what it means when we say this is an infinite dimensional vector space. You guys heard of infinite dimensional vector spaces before? Anywhere? Some have. Maybe. That's what it means, okay? It's not that you can visualize, it's not like the tuples, where n's going to infinity somehow, 3 and n and infinity, but it's just a function that needs an infinite number of basis vectors to expand it, okay? So this is an important consequence. Note infinite number, countably infinite, whatever it's worth. K is element of the integers. So infinite number of basis vectors. So now we can do a direct comparison with, say, ordered triples, arrows, and function as vectors. I think we'll have that here, we'll line that comparison up. Oh, actually, I had one more thing to put there first. Yeah, so this is the one we're familiar with, 1 over 2 pi, right? What if we wanted the more streamlined version without the 1 over 2 pi in front? In that case, we're just going to redefine our basis vector. So I'll just put this as an addendum here. So I'll just rewrite it for f g equals just integral f star of x, g of x dx. This one, let e sub k equal 1 over root 2 pi e to the I kx. Let's call this e sub k of x be the basis vector. And that takes care of that 1 over 2 pi. You just define it in there and it's all the same. Other than that. But we'll use the 1 over 2 pi version for now because that's what we studied earlier. So let's compare this whole thing. I'm going to erase these. We'll compare it to vectors, arrow style, and then we'll compare the Fourier expressions. So comparison. Yeah, so suppose we have A equals A sub x I hat, A sub y j hat, A sub z k hat. And we could get some slightly more general form of this. A sub 1, I'll just say E hat sub 1, A sub 2, E hat sub 2, A sub those are my three unit vectors, I, J, and K, just rename them. Then, what if I wanna find one of these things? Then I can do this, for A equals sum over A sub J, E sub J hat. And now I went from 1 to n, instead of 1 to 3, but of course 1 to 3 is just as good. 3, 1 to n. Then if I multiply E sub k hat to this vector A, what does that do? I'm multiplying a unit vector to this vector A from the left, sum over J equals 1 to n, E sub k at A sub j, E sub j at equals sum over, I can just do that, E sub k at dot E sub j at. And what I have here is mutually orthogonal unit vectors. So this E sub k hat, E sub j hat just turns into delta kj. It's either 1 or 0, and it's only non-zero for k equals j, for j equals k, so that pulls out that A sub k. So what you have is just unit vector into A gives that component. That's a k there, k sub k there. So this is with arrows, and this is literally what happens with your I hat, J hat, K hat, but I just wanted to generalize it to more dimensions. Okay. So let's do the same thing with the inner product space and see what happens. So we'll start here, okay? Actually, we'll start right here. So we have f of x equals the sum over k equals minus infinity plus infinity c sub k e to the I kx. And then we want to do e to the I. Since I'm using k there, maybe I'll use j, not using k. Keeping the letters the same. J. We can do that. So e to the I kx into f of x. That's that function, right? Inner product of that unit vector type of function with this here. So we have 1 over 2 pi integral minus pi to pi, and then e to the minus I kx. And then in here I have to have that sum. So I'm going to go ahead and write the entire sum. J equals minus infinity plus infinity. C should have been a J right here, guys. C sub J. C sub J. E to the I jx dx. Okay, then we'll do a couple steps now, because now this is just the sum. So we'll do sum over C sub J, double J's. 1 over 2 pi minus pi to pi. again is gonna turn into the delta JK. And when you do a summation, sum over J, C sub J, delta JK. This is only equal to 1 when J is equal to K. So that pulls out the C sub K. So yeah, we have the complete analogy to what we can do with our arrows and our inner products, right? Arrows and scalar products. We get the same thing here. Good. Let's see where that's going to take us. One more. It's kind of a big calculation. Okay, so got that. Let's see here. Okay, good. So then. Let's save this for next time. Let me just add a couple problems to our list there. Yeah, last year, I'm just gonna add a homework problem of the geometry kind. I asked you guys for that angle across the diagonal. Let's just add a couple to that. So all good. This is a good place to stop on this right here. So I had given you guys one of these. Add a couple. So we have the cubes. Here we go. So this is the vectors in geometry. These are fun. So instead of doing one, we'll just do 3. So what I had was in my picture, my cube isn't going to be that good. Well, let's give it a try. So we've got X, Y, and Z axes here, and we had that cube. It's going to be. This will work, right? That's a cube right here. Could have been worse. There we go. So I'm gonna let theta AB, theta AC, theta BC. So I can sketch these a bit. This is A. And then I hat plus J hat, the X and the Y, so that's B. So that's A, that's B. And I plus J plus K ends up right there. So theta AB, BC, AC. That's theta AB. This really makes the point of what I had just done earlier, okay, in terms of scalar products. So if I had assigned one of those last time, I think the diagonal would have been, BC. What was that? Well, we'll see. Just go ahead and have these.
Been AC.
Would have been AC. But this is formulated better, and you can really see that, you know, you've got these three perpendicular vectors, you just, you know, get whatever you want that way. And remember, what you're doing is always, you know, A dot B equals magnitude A, magnitude B, cosine of theta AB. Actually, now I'm drawing those norms, okay? So we could, but we're not going to this time, we could also define angles between functions. That's actually done in a lot of applications, angles between functions. Because, you know, once you have a norm, or I'm sorry, once you have FG, you know, you can say that's FG cosine of the angle between F and G. Can't see it, but it's there. We'll do those later. For now, we'll just do these with these arrows. All good. Thursday is all reviewed anyway, okay, and then we'll figure out what's going to be on the exam. But this actually brought us, you know, this brought us back to our Fourier series and stuff. That's not bad. Good.